Okay. Thank you for this opportunity. What I'm going to do today is introduce you to Cascadia, although I'm going to do it super fast and superficially, and really highlight what I want to highlight are a lot of the cross-cutting activities and themes that are happening already in Cascadia, and ask you to think about ways that SZ4D investments could fill in a lot of the gaps. This is just a map of Cascadia and some of the salient features of the subduction zone. I apologize up front. I may give volcanoes a bit of a short shrift. I'm not a volcanologist, but I'll do my best. It is warm and it's a young subduction zone. It's warm. It has a very thick sedimentary prism. Unlike Chile, as has been mentioned, the last probably magnitude greater than 8 or even less earthquake was in 1700, as opposed to every 12 years, as in Chile. This is a challenge, and we'll return to this later on. And you can see the rest. It's a sort of overall a very temperate climate in the forearc and a lot drier in the back arc. Okay. So I'd like to highlight and not go in any detail in any of these, that there is a whole wealth of existing data to be mined and made use of. Some of the examples are shown here, covering all aspects. This certainly can be augmented in big ways, but just again, there's a really firm foundation to work from, again, in all the different disciplines. One of the things that's needed, and this is an attempt to do that, is to put these together into a way that makes it accessible and usable in modeling and for these cross-cutting themes. This is an example of an effort to do that. This is earthquake-centric, but not completely. It certainly addresses a lot of the land and seascape needs. This is really a data portal that attempt to bring together all the different data sets that can be addressed to look at megathrust earthquakes, both from a modern and paleoseismic sense. There's the URL if you want to take a look at it here. This is just an example of, I think, a direction we might want to go, and there's a lot that could be done in this arena that SZ4D could really contribute to. There is also, we have the mega array or the multi-array already in place to some degree. Lots of ongoing continuous monitoring, some of this way back to the 1970s. There's, oh gosh, seismic, geodetic, strain. There's all kinds of climatic data and environmental information, volcanic monitoring, and even a little bit of offshore. There's 2 cables, which I want to just emphasize. They monitor many different things, and there is room to grow. So this is something that a big place where we could really make some strides at relatively low cost in offshore monitoring. Okay, so what I'm going to do now is walk through a series of efforts underway in Cascadia that address these cross-cutting themes. The first one is climate variability, and these are all the other, so this is for those of you who haven't read the implementation plan, probably nobody. This is this famous diagram of the cross-cutting themes, and I've just circled the ones that this particular effort addresses. This case, the land and seascapes and faulting. Anyway, you can see them in the circles. What I want to emphasize is that there are many things going on that we can be leveraging. This is a project, an NSF-funded Coast and Peoples project to look at Cascadia geohazards. There are 5 elements, and one of the things that this could be, that SZ4D could learn from in this, is there's a big social science component in this effort. They're trying to combine tectonic and climatic modeling and data integration with assessment of hazard along the coastline. And again, there's a big, this map here, these circles are communities that the social scientists and the scientists are engaging with in Cascadia to get this work done. And I'll show you an example of one of the outputs. And this is only, project's really been underway only a little over a year. This is map here on the left. The circles are all the they've compiled all the observations of vertical land level changes from tide gauges, GNSS, et cetera, and some tectonic coupling models to make, and climate models of sea level change to put together the best assessment possible to date about what sea level rise is likely to be along the coastlines in the near future. This has been a collaborative effort with both local to federal institutions and groups. Another potentially, because this is not yet supported, as this has been mentioned already, collaborative complementary effort is this Crescent proposal. This is a response to the NSF call for an earthquake science center. This has like these circle diagrams, just like SZ4D. And there's a couple things I want to point out in this is that there's again a big, just like SZ4D, a workforce development component and community collaboration or collective impacts component. There is no data collection or infrastructure in this proposal. So this is a real opportunity to combine the analyses and data integration proposed in this with some of the instrumentation and infrastructure development proposed in SZ4D. Okay, so the next effort is focus on triggering and cascading, cross-cutting theme, is on triggering and cascading hazards. And this brings us to volcanoes and land and seascapes. This is a picture of Mount Rainier. It has erupted 40 times in the last 10,000 years. Lahars are a really big issue on Rainier. 9 of those in the last 5,600 years have reached areas that are now very heavily populated. And this was recognized not very long ago, and there's really been a collective effort, and this gets to the collective impacts component of SZ4D at the county to the federal level to do something about this, not just study it, but actually do something. And this required, again, a very holistic approach. This is a report that just came out last year of modeling of where these lahars, as well as other hazardous phenomena, may occur due to Mount Rainier's volcanism and the heavy rainfall. So these models have led to these maps. This is a publicly available and meant for planning of the modeled debris flows, lava and pyroclastic flows, and lahars. And this has led to the installation of a lahar detection system. This is shown schematically here. This is now a really well-monitored volcano as a result of driven really by the hazard. The green dots are sites that are installed, and you can see the many types of instrumentation in green. There are stations already, other additional sites in the works, those are in blue, and then more proposed. So this is ongoing and really is an effort of an example of successful, in my mind, collective impacts. Okay, another example is in forecasting and prediction. And this is driven by the need to understand megathrust earthquake recurrence. What has been long noted, even though Cascadia has probably the best paleoseismic record of anywhere except for maybe Japan, there is a big discrepancy, big in the sense it has a the difference between the offshore record as defined by turbidite interpretations and the onshore record as defined by tsunami and coastal uplift and subsidence observations. There's a big difference in the recurrence estimates. This has a big impact, 40% difference in the hazard depending on which recurrence model interpretation you choose. So we've been tasked to sort this out. And in addition to, despite having this great paleoseismic records, there's still more that could be learned. This just shows, again, in another way, all the paleoseismic sites are in dots, onshore in black and blue, offshore, those are turbidites. We still cannot rule out the possibility that the last earthquake in 1700 was a single earthquake or potentially multiple sequential earthquakes. This already has been shown. Gavin showed this. This is some new possibility, a new type of data and analyses that comes from a new landslide inventory. The dots are the onshore. This will be published very shortly, and an offshore inventory of offshore landslides from the latest and greatest bathymetry. And by combining with this with some dendrochronology, they've learned that, lo and behold, not a single, there's some 20-some dates now of landslide dammed lakes. Not one is associated with 1700. And basically, this has shown that the climatic signal is way bigger than the tectonic signal. This provides some constraint on the frequency of megathrust earthquake shaking. They're also looking at some coastal landslides that could only have been occurred as a result of shaking. The climate forcing is simply not great enough. This provides a minimum estimate of shaking in past earthquakes. Another way, a new type of constraint, is from looking at what's called fragile features. This is a C-stack. And by combining this with stability modeling, we can use this to provide a constraint on the maximum shaking that could have occurred and leave features like this still standing. So new types of studies that can be pursued and are being pursued. And lastly, on this is this amazing, this was just recently published by Hill and others in 2022 of offshore this shows the value of offshore high resolution bathymetry data. This bathymetry has now been used to map the landslides, as shown densities here. And this is going to be correlated with potential models of the shaking and to learn about the stability of the offshores and how sediment is transported and so on. This is already causing us to rethink some of the interpretation of the offshore record in terms of earthquake recurrence. So this is really being transformational in how we think about recurrence here. And finally, in this arena, these data, the paleoseismic data, are being used in ground motion models as well as tsunami generation models. This is work of Diego Melgar, who's used these paleoseismic data to constrain the models, and shows that still, even given all this data, it's still possible that the 1700 earthquake was a series of earthquakes rather than a single full margin rupture. Okay, the next cross-cutting theme addressed is mass and energy balance. And again, this links everything but the volcanoes in this case, and focuses on the offshore. This is a pilot study that was done in 2019 by Andrea Ogston and others, where they instrument to look at sediment flow from the channel head all the way, in this case, just the channel head. They actually monitored sediment input in Astoria Canyon, one of the major canyons, and showed even during the wet seasons, there were pulses of sediment delivered to the offshore. This has now been funded by the NSF to do a more expanded version and look at the sediment input farther down the channel and over a full climatic cycle. And finally, again, Gavin showed another image like this there is now in southern Cascadia some super high resolution imagery, bathymetry, as well as coring that is really now giving us a view that's comparable to what's possible onshore. And this is revealing, we can now answer questions about splay faulting, and with this dense sampling of cores, address some of the big uncertainties in how we interpret the turbidite record. So this again is transforming how we think about recurrence. And finally, a cross-cutting theme of rheology and stress. This is 2 maps on the sort of long-term timescale. This was mentioned by others. Whoops, sorry. We know there's largely due to the lack of data offshore. 2 minutes, okay. We have a wide range of uncertainties in coupling. This is being addressed by the installation of GNSSA. Gavin already mentioned the community experiment for GNSSA, so I'll skip that. There was a large experiment where we can look at structure and its impact on rheology and stress and the material properties. And I just want to highlight a really cool observation from this experiment in the offshore component, where they've looked at spectrograms of shaking. This is not strong shaking, and can look at these bands here are resonances, and they change in frequency with time. Basically, what they're seeing is a nonlinear response of the sediments. So this is not something that was anticipated, but is a different use of these kinds of data. So there's all sorts of things that can be explored. Finally, I want to end not with a summary, because you've just seen all this stuff, but the other transformative element of SZ4D is the ability to look globally, or what Emily calls subductology. And I want you to, I'm going to task everyone to go forward and think, how can we make measurements and what can we do in Cascadia that will allow us to look at subduction zone science globally? And I'll leave it at that.